In the previous lecture, we were discussing homogeneous equations, homogeneous ODEs, ODEs. We used substitutions to solve such kind of ODEs, homogeneous. We check, in fact, the degree of each term in this first order differential equation, and then we make a substitution accordingly of this form: y is equal to u times x into x, or we make a substitution of x is equal to u times y. Sorry, not this one, v. Here we had v of x. V of x, no, y of x. Yes, it was correct. यहाँ पे y of x था, यहाँ, yes. It was v of y and it was substitution of x. So we can make one of these two substitutions in homogeneous differential equations in order to transform those equations into separable ODEs. Today, we are going to discuss a couple of more ODEs, special ODEs, in which we use the substitution. All these ODEs, they basically fall into a category of first order differential equations where we use substitution method. Okay, so as we have used substitution in this differential equation in order to convert this differential equation into separable so that we can solve it. Okay, otherwise we cannot solve directly homogeneous ODEs because they are nonlinear ODEs, first order ODEs. Another kind of ODE in which we can use substitution method. In fact, these are all equations where we use substitution method. So we can say it substitution methods for solving first order ODEs. Okay, that also fall into this category. Now, if we have, for example, category 1, if we have an equation of the form, for example, dy by dx is equal to some function of a times x plus b times y plus some constant, and the function is of this form, that is, we have this expression in the function. Okay, it's a function f. It is a function of this variable. For example, let me give you an example of this thing. Example of solve the following differential equation: dy by dx is equal to 1 minus x minus y over x plus y. Okay, if you look at closely this function, it can be written as it is 1 minus x plus y divided by x plus y. So in fact, it is a function of what? Function of x plus y. Okay, if we assume that this x plus y is some other variable, maybe u, okay, then it can be written as 1 minus u divided by u. If we assume that this x plus y is equal to u. Now, here we have dy by dx, here we have 1 minus u over u. So this right hand side is a function of u and the left hand side is a function of x, okay, because it's a y depending on x. So if we have an ODE of this form, and of course this is neither separable, this is not linear, okay, we cannot solve this differential equation directly by using method of separation of variables, or we cannot use integrating factor in order to solve this differential equation. But we can see that this function, so this differential equation, the right-hand side function is, in fact, it contains x plus y. Okay, so this whole function is a function of x plus y. Now, what we do in order to solve such kind of differential equations, we make a substitution. We make a substitution. We say that let u is equal to ax plus by plus c. Okay, then this function becomes a function of u, f of u. But if this function has been converted into a function of u, then we also have to convert this thing. Okay, how do we do here? If we make a substitution u in terms of x, then in terms of x and y, then we have to also use, if u is equal to ax plus by plus c, then we have also du by dx. It is what? A times x1. हाँ, बाकी टर्म 0 है, ठीक है. तो यहाँ पे x का डेरिवेटिव 1 हो जाएगा प्लस b times y, b times dy by dx आ जाएगा, because we are differentiating both sides with respect to x. Okay, plus the derivative of constant is 0. So du by dx is in fact a plus b times dy by dx. Okay, this is our dy by dx. Okay, sorry, here we have u, du by dx, not y. It's du by dx. So the whole equation, the equation was dy by dx is equal to f of ax plus by plus c. Then this dy by dx will be converted into what? It will be, you can say, du by dx minus a into 1 over b. Because we can find the value of dy by dx from here. And we put it equal to f of u. Now, this whole equation has been converted into a new variable u, which depends on x. Okay. Now, you can see that this equation would be either a separable differential equation or a linear differential equation. Most probably, it will be a separable differential equation. Okay, which can be solved now by using either separable of variable technique or by multiplying integrating factor on both sides. Let's do this. Let's apply this technique on the example above, this one. Now, 1 minus u divided by u, we substituted u is equal to x plus y. Now we are going to convert this thing using this substitution. So u is in fact a function of x by. So it is x plus y. Du by dx, differentiating on both sides with respect to x, 1 plus dy by dx. Okay. So from here we can find dy by dx, which is equal to du by dx minus 1. So the equation, which is dy by dx, is equal to 1 plus u divided by u. In fact, it was what? It was 1 minus x plus y divided by x plus y. So if we use this substitution in this one, we can write dy by dx is equal to du by dx minus 1 is equal to 1 minus u divided by u. Okay. Now you bring this 1 on the right hand side and take LCM. So du by dx is equal to 1 minus u plus u divided by u. Okay, I took the LCM. So you cancel, what do you get? 1 by u. So this equation du by dx is equal to 1 by u. It is separable now. Separable ODE, which can easily be solved by using separating the variables. So it becomes u du is equal to x, no, 1 dx. 1 dx. Okay, integrating both sides. So what do we get here? Dx plus a constant of integration. And then the left hand side becomes u squared by 2 is equal to x plus c. Now you had that substitution, u is what? X plus y. Once you solve the given equation, you have to substitute back the assumption or the substitution you made into the given differential equation in order to get the solution in terms of x and y. Okay? Because the original equation was in x and y, so the answer, your answer should be in x and y. So it becomes x plus y whole square divided by 2 is equal to x plus c. So you can leave it here. It is your answer. It's an implicit kind of solution. I hope you get it. If you have any question, you can ask me. Let's see a couple of more examples of these kind of differential equations where we can use the substitution. Yes, why not? Let me clean this board. Maybe let's come to the other board. You can see it. If you have any question, you can ask me. Examples. I hope you can see the board.
Yes, sir, we can.
You can try this, try to solve this thing. dy by dx is equal to tangent square of x plus y maybe. And dy by dx is equal to maybe 3x plus 2y minus 7 divided by 1 minus 3x plus 2y whole square. Okay, you can try this one. You can see that this, you can make a substitution of 3x plus 2y. In square root also, you may have a square root of 1 plus 3x plus maybe 4y. Okay, you can make a substitution of all this thing. Okay, similarly, many other examples can be given. I hope you can find more examples and exercises in the book. Try to solve these equations. Now, another kind of differential equation which can be solved by using a particular substitution is the Bernoulli equation. I hope you can do it. If you have any question in these kind of differential equation, you can ask me. Try these examples. If you face any difficulty, you can ask me question in the next lecture. Or I'll definitely advise TA to do a couple of these kind of equations in the next tutorial for your practice. The next is Bernoulli's ODE equation. It is also a first order differential equation. Bernoulli was a French mathematician in 1695. I think he born. He was a French plus Swiss mathematician. He gave this. He gave the solution of this differential equation, which later on called the Bernoulli equation. It's a kind of linear equation, but it's a basically linear equation plus some kind of non-linearity on the right hand side. So the equation of the form dy by dx plus p of x y is equal to f of x times y power n. This is not exactly linear equation, but it's a kind of linear equation with the non-linear term on the right hand side. The left hand side is a linear differential equation as we had discussed. The right hand side has some function of x times y power n, where n is some integer. Okay, y is some integer, or it could be anything. So how to solve this differential equation? We also use the substitution method. What do we substitute here? In fact, Bernoulli divided this whole equation. For example, we call it 1, divided this whole equation by y power n. So if we divide this whole equation by y power n, means the right hand side, this y power n, you have to divide this whole equation by the y power n, which arises here. So if we divide it, we obtain this thing, sorry, plus p of x into y divided by y power n is equal to f of x. Okay, now which can be written as y power negative n dy by dx plus p times of x y power 1 minus n. Well, when we take this n in the numerator, it becomes 1 minus n is equal to f of x. Okay. Now, what substitution we use here in order to transform this differential equation into separable, or no, not separable. It will be converted into a simple linear first order ODE, which can be then solved by multiplying it with the integrating factor. Now, what substitution we make here? We make a substitution, substituting or substitute u is equal to what? U is equal to this thing, y power 1 minus n. Y power 1 minus n. We substitute this. Remember that here u is a function of x and y is also a function of x. Okay, so we put y power 1 minus n is equal to u of x. Now we have to convert. Once you try to make a substitution into a differential equation, then you have to convert all the variables into a new variable. Okay, if you are going to substitute y in terms of u, then you have to convert all the y's into u. So here, y power 1 minus n will be substituted as u, but here we have y power minus n and dy by dx. Okay. Now, differentiating on both sides with respect to x, differentiating with respect to x on both sides of this substitution, what we obtain, it's du by dx is equal to, here you have power rule, you have to apply a power rule. Power comes down, y power 1 minus n minus 1 into dy by dx. Okay, because y is a function of x, then you have to apply the chain rule. So you have to take dy by dx further along with this after applying the power rule. Here, this one will be cancelled with this one, And what do you obtain here? 1 minus n times y power minus n dy by dx. Now this is equal to du by dx. Now you can see here, this whole term arises here. Okay. Now you can substitute this equal to 1 by 1 minus n times du by dx by using this expression. Now, using this substitution and this expression, we can convert this whole differential equation into a new differential equation, which is now 1 by 1 minus n du by dx plus t times x times u is equal to f of x. Now, what type of differential equation is this? It is linear differential equation. So it becomes du by dx plus 1 minus n times p of x times u is equal to 1 minus n times f of x. Okay, which is simple linear first order ODE, okay, which can be solved by multiplying it with the integrating factor. Now, this is a new linear ODE, first order ODE. We can solve this differential equation by finding the integrating factor and then multiplying both sides of this differential equation with the integrating factor. Okay, I hope you can do it. Let's try some examples. And later on, after solving this differential equation, you have to use the backward substitution. You have to put u is equal to y power 1 minus n again, in order to get the solution in terms of x and y. So, let's try this example. Start from here. At 8:40, remind me, I'll start the quiz. Solve the following differential equation. Solve dy by dx is plus minus y is equal to e raised power x y power 2. Now, nobody will tell you solve this Bernoulli first order differential equation. Okay, I'll simply ask solve this differential equation. This is you who have to judge whether this is Bernoulli differential equation or not. Okay, you can see that here you have dy by dx. The left hand side is a linear first order ODE. The right hand side has some function of x times the power of y. So if you see any differential equation of this kind anywhere, you have to use this method. You have to, you should know that this is a Bernoulli first order ODE, and you have what substitution you have to make. You have to remember this. So what was the substitution? In fact, we substitute u of x is equal to y power 1 minus n. What is n here? It is 2. So this is your n. It is 1 minus 2, means you have to substitute 1 power y power 1 minus 1, or you can say 1 over y in short. Okay, you have to make this substitution. Now differentiating on both sides, du by dx is equal to what? It is negative 1 by y square dy by dx. Okay. Now, if 1 by y is u, okay, you have to, or you can say that you have to divide this thing over here it will become 1 over y square dy by dx minus 1 over y is equal to e raised power x. So now you have this equation. Now 1 over y square dy by dx is equal to what? It is du by dx. You have this thing extra here, negative sign. You take this negative sign here, then you can put here plus and negative here. So by using 1 over y is equal to u and 1 over y square dy by dx square dx is equal to negative du by dx. You use these substitutions expressions here in this differential equation, and you will get minus du by dx minus u is equal to e raised power x. Okay. Now, further, we can write du by dx because we have to convert this differential equation into standard form first. The coefficient of du by dx should be 1 in order to make it first order linear ODE. So du by dx is equal, plus u is equal to negative e raised power x. Okay. Now, this is linear first order ODE. This is linear first order ODE. We can solve this ODE by finding first the integrating factor. Integrating factor is what? E raised power integral p of x dx. Okay. What is p of x in this differential equation? What is p of x? In fact, the p of x arises here. The coefficient function of u, it should be p of x. It is what here? It is 1. So p of x is 1 here. So the integrating factor is 1 dx, which is e raised power x. So your integrating factor is e raised power x. But we don't add a integration constant here. I told you in the previous lecture why we don't add a constant here. Now, multiplying the equation with the integrating factor, we obtain this thing negative e raised power. यहाँ पे x था, यहाँ पे e raised power x एक और हो गया. Right hand side पे negative e raised power x ही था ना? हाँ, this one is the negative e raised power x. Now, the left hand side must become the product of integrating factor times the dependent variable, okay, according to the linear first order differential equation. And the right hand side becomes negative whatever it is, e raised power 2x. Now integrating both sides with respect to x, we integrate with respect to x to both sides, and then add a constant of integration here. Here on the left hand side, the derivative and integral will be cancelled out according to what? First fundamental theorem of calculus. First fundamental theorem of calculus आपने पढ़ा होगा calculus में. We use sorry, first fundamental theorem of calculus here, and we obtain e raised power x u times u is equal to negative e raised power 2x divided by 2 plus c. Okay. Now, u of x is what? U of x is, you have to divide this thing on the right hand side. It becomes e raised power x divided by 2 plus c times e raised power minus x. And you divide e raised power x on the right hand side. Now, you have to use backward substitution because this answer is in u in terms of u and x, but you have to find the answer in y and x. So backward substitution, you have to put u is equal to 1 over y because u was assumed to be 1 over y. So we obtain this thing. So this is your solution, which is a kind of implicit solution. Okay.
Sir, I have a question.
जी बोलें.
सर पिछले बोर्ड में बेर्नौलीज इक्वेशन में आपने dy बाई dx को किसी चीज से रिप्लेस क्यों नहीं किया?
चले देखते हैं कहाँ पे रिप्लेस नहीं किया यार, कहाँ पे, यू टेल मी।
सर ये जो एग्जांपल में आपने लिखा है ना 1/y², तो आपने 1/y² को तो रिप्लेस किया है du बाई dx से, लेकिन जो उसके साथ dy बाई dx है वो कहाँ गया?
ये इसके साथ ही है ना बेटा, ये देखिए 1/y² dy बाई dx, ये पूरा रिप्लेस होता है माइनस du बाई dx। We used these two expressions, these two, यहाँ पे ये वाली जो u की जगह क्या आ गया, यहाँ पे देखिए 1/y की जगह क्या आ गया, u, 1/y की जगह u आ गया, और फिर 1/y² dy बाई dx, इस सारे की जगह क्या आ गया, 1/y dy बाई dx, इस सारे की जगह क्या आ गया, माइनस du बाई dx, तो इसकी जगह माइनस du बाई dx आ गया।
सर जब आप डेरिवेटिव लिया तो साथ dy बाई dx क्यों आया और कैसे आया?
यहाँ पे we take the derivative of this thing, u is equal to 1/y, इसका डेरिवेटिव लें दोनों साइड्स पे विद रिस्पेक्ट टू x, तो du बाई dx यहाँ पे आएगा, यहाँ पे क्या होगा, 1/y का डेरिवेटिव विद रिस्पेक्ट टू x क्या होगा, y की पावर, y की पावर -1, वो -1 नीचे, फिर -1 -1 -2 आ जाएगा, और फिर क्योंकि y फंक्शन है x का, ठीक है, हम डेरिवेटिव ले रहे हैं विद रिस्पेक्ट टू x, नॉट विद रिस्पेक्ट टू y, so we have to apply the chain rule। तो पावर रूल जब फिनिश होगा ना यहाँ पे while taking the derivative here, let me do it again for you so that you can understand it। again यहाँ पे डिफरेंशिएट किया हमने with respect to x on both sides, differentiating with respect to x on both sides, okay। इधर लेफ्ट हैंड साइड पे तो du बाई dx आ गया क्योंकि ये न्यूमरेटर में है। अच्छा यहाँ पे y पावर -1 है, इसका आपने डेरिवेटिव लेना है विद रिस्पेक्ट टू x, ठीक है। अब डेरिवेटिव है विद रिस्पेक्ट टू x, यहाँ पे तो वेरिएबल y है, y के अंदर x वेरिएबल है, y इज अ वेरिएबल ऑफ x, ठीक है। यहाँ पे y का डेरिवेटिव रिस्पेक्ट टू x नहीं ले सकते आप, आपने क्या करना है, यहाँ पे चेन रूल अप्लाई करना है। चेन रूल क्या होगा, dy by dy of y पावर -1 टाइम्स dy by dx, ऐसे चेन रूल अप्लाई करते हैं ना। अब यहां पे आप डेरिवेटिव ले सकते हैं विद रिस्पेक्ट टू y, ठीक है। ये वाला जो dy by dx है इट विल स्टे अलोंग, ठीक है। तो यहाँ पे इसका डेरिवेटिव क्या होगा, इसका डेरिवेटिव होगा पावर रूल, पावर नीचे, पावर में से एक माइनस, ठीक है। बस ये खत्म हो गया, इसका डेरिवेटिव, पावर रूल अप्लाई हो गया, टाइम्स ये जो dy by dx है ये साथ ही रहेगा। आई होप यू कैन सी दिस, who was asking this question?
Yes sir, I can see it.
Now this has become -1/y² or dy by dx, okay। So the whole thing du by dx is equal to -1/y² dy by dx। अब ये जो सारी है, ये जो सारी चीज है 1/y² dy by dx, यहाँ पे ये सारी है ना 1/y² dy by dx, इसकी जगह हमने क्या पुट कर दी, इसकी जगह हमने यहाँ पे, अगर आप इसको यहीं पे देखें तो यहाँ पे हमने पुट कर दिया -du by dx, क्योंकि किसके इक्वल है, यहाँ पे माइनस एक एक्स्ट्रा है ना, तो ये माइनस हमने इधर लगा लिया, बिकॉज वी नीड ओनली 1/y² dy by dx। तो 1/y dy by dx की जगह आपके पास du by dx है, माइनस 1/y हमने अस्यूम किया था क्या, 1/y is u, so this becomes u equal to, राइट हैंड साइड क्या थी, e raised power x, यहाँ पे e raised power x. So our equation has become now this thing, which is a simple linear first order ODE. And we can solve this ODE by finding first integrating factor and then multiplying integrating factor on both sides, and then doing the same procedure we do usually for solving first order ODE, linear first order ODE. I hope you get it. If you have any other confusion, you can ask me any question. Okay, that's fine. I hope you can do it now. Bernoulli's first order ODEs or Bernoulli's equations. This is the procedure for solving Bernoulli's equations. So remember the form of the Bernoulli equation, it should be dy by dx plus p of x times y. The left hand side is same as the first order linear ODEs. The right hand side contains an extra term of this kind, some function of x times some y powers. Then this equation is basically Bernoulli's equation, and we can solve it by using substitution of this form. Okay, so this kind of equation also fall into a category of substitution methods. Okay, whenever we use some substitution in order to solve these kind of differential equations, this is called substitution method. If you have any question, you can ask me. And why do we use these kind of substitutions? We have to solve these kind of differential equations. We are lucky enough that someone has already invented these substitutions. Otherwise, we had to do it. And it is very difficult to find an appropriate substitution in order to convert some particular differential equation into another kind of differential equation, which can be solved easily by using existing techniques. In the next lecture, we shall start exact ODEs. So for today, it's sufficient for today. Now we are going to start the quiz. The quiz will start at 8:40, and I have to give some instructions to you people as well before starting the quiz. So I'm going to stop this recording. It will be today's lecture. I shall upload it later on. If you have any question regarding today's lecture, you can ask me.